So let's pick up with our discussion of OSPF neighbor selection. Now, one of the things we mentioned that gets sent in every hello packet is the router ID. And the router ID is how OSPF routers identify themselves to one another. Obviously, since every OSPF router knows about every other OSPF router in the network, or at least in the area it's in, OSPF has to pick an identifier that is fairly static. Now, by default, OSPF takes the highest IP address configured on the router as the router ID, with just one little modification to that rule, and basically loopback interfaces always win even if they're not the highest IP address. Now, if you have multiple loopback interfaces, it will take the loopback interface that has the highest IP address. And the logic behind that is loopback interfaces are designed to be accessible from any interface on the router that happens to be up. If you think about a typical WAN router, you have a serial interface or an MPLS or whatever the interface is connecting you out to the carrier network, and then you have an Ethernet interface that's on the local area network. Now, if you use the address that's on the Ethernet interface on the local network for your management, then if that interface ever goes down, i.e. the switch it's connected to gets powered off or someone unplugs the cable, then that address is no longer valid because that interface is no longer valid according to the router. And so therefore you won't be able to get to it using its Ethernet address. You'll have to come in through the serial interface. If you have a loopback address, however, you can always get to that address no matter whether you're coming from the Ethernet side or from the serial side. And so that's why OSPF picks the loopback interface for the router ID if one's present. Now, some of you may already see the fatal flaw in this, in that if the highest IP address ever changes, the router ID could change and could cause routing instability. Now, in reality, the router ID is picked when OSPF initializes, and it doesn't change even if any of the IP addresses change unless you force the process to clear all of its databases or you power cycle the router. So you could run into a situation where you're expecting an OSPF neighbor to be on a certain IP address, so maybe you have access control lists built or you have authentication built around that specific IP address or that specific router ID. If the router ID changes, then you could have a network situation where you're not actually using that router because the rest of OSPF is not expecting to see that router. It's for this reason that you can, and probably should, manually set the router ID in the OSPF process. When we go through the lab, we'll show you how to do that. It's a pretty brain-dead command. You'll kind of laugh when you see it. So finally, let's talk about the stages of an OSPF neighbor relationship. The first stage is the init stage, and the init stage basically says, I've sent a hello packet to a neighbor, but I've not received a hello packet back with my router ID in the neighbors or scene field. And then we have two-way, which is, I've received a packet back with my router ID in the scene field. Now, it's important to remember that the neighbor checks are performed every time a hello packet is received. And so if these checks fail, the neighbor will stay in the init state. You'll see it referenced as stuck in init. So that means, for example, if you go on a router and you change its authentication information, or you change the subnet it's in, or you change the area ID for a network, then all of the neighbors, the next time it gets a hello packet 10 seconds later, will say, hey, these parameters don't match, I'm not in the same area, I'm not in the same subnet, so on and so forth, and that router will drop out of OSPF, and you'll look on the other routers and you'll see it, but it'll always be in init, and we'll actually see that when we break our lab here in just a little bit. Now, I've got a little diagram here that describes how all of this works together. So let's say we've got two routers. We've got 9876 over here on the right and 19.18.17.16 over here on the left. I'm very, very creative with these router IPs, you can tell. So when this router on the right comes up, it sends a hello packet that says, I've not seen any routers. My router ID is 9876. This router over here receives it, does all the neighbor checks, and says, yes, everything checks out. We can be neighbors. So it sends a hello packet back after 10 seconds saying, hey, I have seen 9876. My router ID is 19.18.17.16. At this point, router 9876 assumes that it is in a two-way communication state with the router over here on the left. So it will get marked as two-way, even though this router over here is still in a init state. 10 seconds later, this router over here sends out a hello packet that says, hey, I've seen 9876 and 19.18.17.16. My router ID is 9876. At which point 19.18.17.16 over here on the left says, hey, I see my router ID in the scene field of this packet, therefore he's accepted my neighbor parameters and we are actually exchanging routes. At this point, both routers say that they are in the two-way state with this neighbor, and they then proceed on to the next stage of OSPF communication, which is exchanging the link state databases. Now, the actual mechanism with which the link state databases are exchanged is a little advanced for the CCNA level. It's not covered in the syllabus for this course, and so we won't cover it here. But again, there are pages and pages and pages of resources on the internet to get you started on this, plus the CCNP course gets into a lot more detail with exactly how the link state advertisements go back and forth. And that concludes our discussion of OSPF neighbor selection.